All right, so wait a minute. Let's make sure it's recording start. Yeah. Okay, good. Right, so let's continue our lecture. I'm sorry for the technical problem. The reason why I forgot my adapter is that last week I went to US, right? I visited several universities, Northwestern, UIUC, MIT, and Brown. Okay, so I need to bring my adapter with me, so I could do the project do the presentation there. Okay, and I have spun some very interesting phenomena during my visit. That is really interesting, and I will share with you maybe later. All right, so let's continue our lecture first, and then we can share some story about my experience in US. Very nice experience. I have learned a lot from other university. The reason why they become top university in the world, there are definitely some problem, something they got something to make them top, and why we cannot be top. We can think about that. Okay, let's go. Right. So last time we talked about integrating factor. So can we make a non-exact function q become exact by multiplying a factor? So what does that mean? Which means that q actually depending on its path when they do the integration. So can we make it exact by changing it?喂，声音那么小，但是又会回音呢？喂，OK. So integrating factor a here. I want to times a here and make it become another function called z. Okay, and we want to see what kind of condition the z can satisfy, okay, to make z exact during the integration. Okay, so z become function of xy, of course, because this is basically the same function of q, but times an integrating factor. So d can be treated as a function of xy, so its change dz can be decomposed into two contribution, dx, dy, and m and n is of course their slope, right? So what is the condition for the differential z is exact? Remember, the definition of the exact integration is that after doing the cyclic integration, c it will make it 0, right? Because initial condition and final condition should be is the same state. So which means that no matter what path they do, during the integration, they always become 0 path independent. Okay, so let's make a really simple condition for the cyclic integration. We start from a to the right hand side and y and x and y. Okay, so it make a really simple way to make it general. All right, so start from here to here to here to here. Right, so the x, a, b, and y is c, d. All right, so let's decompose ab and ba. Okay, a, b, and b. Sorry, let's go first. Yeah, it's okay. Sorry, wait a minute. I can. Yes. Right. So I can make it. Right. So let's write down. So your M, AB, and BA. Okay. This one can be written down as AB M X C dx plus BA M X D D. Wow. M X D dx. Right? And we can notice that this is actually the AB's blue, yellow and blue. Right? You can understand N and N to do the cyclic integration. Right? So let's continue. So what it looks like is, let's continue. It actually become, well, we don't have enough space. So, but to make it continue our calculation, minus N A Y D. Okay, and it will be C D A B partial N partial X dx dy. All right. Good. All right. So sorry for not enough space, but actually this one will, how to do that? Okay. And this one equal to A, B, and XC minus M X, okay, D dx equal to A, B, D, C partial N over partial Y dy dx. Okay, let's explain this a little bit. Okay, so I believe you understand this one, right? Then we just combine them together. Okay, be dy dx dx. All right, so it looks very simple. You see, nby nay is actually the equivalent to you do another integration. You examine this part and that part. Actually, they are the same, right? So, well, I'll try to make it easier to understand. Right? So you see, this is a partial n over partial x to a to b and d to c, c to d. So it can be directly written down to here. Okay, this is actually a area integration. Okay, dx dy. Right. So this is the first part. The second part here is that after you do the integration, you do dx out of the brackets, and then you see this part. Anything else? Any grade? It's actually this one. Okay, so but notice that because the minus MD here, CD, A, B to C, A to B, which is you need to do the CD first. Sorry, wait a minute. So this is a CD, but you need to become, you see this A, B, and C to D, C to D, but here is D to C. So you need to give a minus sign here. All right, so you need to be really careful about this. Because your integration is A to B, C to D, but here you're A to B, but here is D to C, so it's kind of reverse direction. So this needs to be careful. This is the reason why there's a minus sign here. All right. So after that, you can make it go to here, and then you can see that the conclusion is that for N in cyclic integration looks like this. For M cyclic integration is this one with the minus sign. All right. So remember that the integration dz equal to 0. So how can it make it always 0? It's because we can say this one equal to 0. All right. So a partial n over partial x minus partial n over partial y dx dy equals 0. Okay. So as long as, well, sorry, I shouldn't write down here. It's not 0. It should be when they sum out together 0. Sorry, I shouldn't write down equal to 0 equals 0. Sorry, I should say summing out together becomes 0. So the requirement, the condition they need to meet is partial n over partial y equal to partial n over partial x. That's it. That's it. All right. So if we can multiply a factor to function of q and make the resulting z satisfy condition like this on the left, then the exact relationship is obtained, held. Okay, so integrating factor can make the z do the cyclic integration become 0, and which means that if the m partial y partial n partial x equal to each other, it can make the integrating factor workable. All right, so this is the math techniques that we will use this later. All right， 好，我们现在要讲的是积分常数吗？哈，那怎么翻呢？积分 factor， 积分的 factor， 这个 factor 它可以乘上一个 q， 然后让它变成另外一个函数，然后这个另外一个函数它会 exact， 也就是 path independent， 不关路径啊，不关路径，在积分的时候要怎么样要怎么样确认这个 a 是正确的？你可以随便乘任何东西，但是什么东西才会让它变成 exact 呢？我们必须要看看它有什么样的条件。OK， 所以我们就假设 a 这样乘上去以后，它 z 的话呢，它的变化是 dz， 然后它就会是 x 跟 y 的两个共线，前面当然是斜率，我相信大家都知道。好，那接下来我们就把 cyclic 的integration 呢写成这样很简单的很简单的最简单的方式 ，ab cd ba dc 这样子 ，OK？ 好，那这时候我们就把黄色跟蓝色先写在这里，这是最简单的，因为它的 c 是 y 在这边是constant， 所以把 c 就带进去了。然后蓝色这边的话就是 d 是 constant 啊 y 等于 d， 然后就把它弄进去。那这边粉红色也一样，绿色也一样，好，就把它写下来。所以这个 cyclic integration 可以把它写成这4个项。好，那我们分别来看上面这2个项呢，我们把 dy 拿到外面去，就看到这个东西。那这个东西其实你可以仔细看一下，钻研一下，你会发现其实这个东西正好就是这个东西的积分的结果，也就是 partial n over partial x 对于 x 的积分结果，而且是从 a 积到 b， 你看 b 减 a 嘛，对不对哈？所以说这个褐色、橘色的这个荧光笔的部分是相等的。好，接下来这个部分呢，又可以写成这样子，写成这个东西。那灰色部分也是 partial n over partial y 之间的就是的积分，而且是从 D 积到 C，D 积到 C，OK？ 好，所以灰色的部分可以写成这样子。但是这问题来了，你看哦，这边的 DC 它是从 D 积到 C， 对不对？可是问题是它这边的，你看这边是 A 积到 B，A 积到 B， 你在做面积分的时候 ，A 积到 B， 如果是用面积分来看 ，A 积到 B 在 C 积到 D 就已经包含了整个面积了嘛，对不对哈？你不能说 A 积到 B， 然后又从 D 积回 C， 这样的那个面积就不顺了，对不对？它会变成一个折的东西。所以说，你为了要把它之后最后变成一个面积分的积分，所以你这边的 D 跟 C 必须要互换，它才会很顺的路径 A 到 B，C 到 D。所以这边的要互换，上下线要互换，一互换以后，这边就多了一个负号。OK， 好，那这边弄好以后，也就是说这一大串会等于这个东西，这一大串会等于这个东西。好，那这一大串会是加起来会就是z 的 cyclic integration， 就是头跟尾相同的积分。那也就是说，这个东西加起来是这样子。那加起来这样子要怎么做呢？它们要等于0，它才会满足它 exact 的条件，对不对？好啦，那所以我要看它这边等于0，这边等于0，要怎么样才会等于0啊？中间这个等于0就好啦，对不对？因为你的 dx 跟 dy 其实是任意数，所以说你这个等于0的话，它的 cyclic 的 integration 一定等于0。所以说，如果今天我乘了一个 a， 然后它里面的 m 跟 n 有满足这样子的条件的话，我的 a 就成功了，成功的让它变成一个 cyclic integration 会等于0的状态。所以说，这个东西是 a integrating factor 它成功的必要的条件。所以我要选一个 a 会让它的 n 跟 n 的关系要变成这样。如果可以这样的话，你的 a 就成功了。然后它会变成让 z 变成一个 exact 的函数。All right, so that's the mathematic 数学的东西就等一下会用到这样。好 ，next the final math techniques I will introduce after the review 1 is the Maxwell relationships. The Maxwell relationship is that you know this, right? Well, we should say later we will introduce this one. du equal to TdS minus PdV. All right. Later we will introduce this, but you can imagine that if you have other function du equal to TdS minus PdV. We don't know it yet. We haven't introduced this yet. But if your du can be written down in other form, but you all know that actually you can imagine that you can see du equal to TdS minus PdV, which means that u equal to u is a function of S and V. Okay, we are not talking about the physical meaning in this page. Now we just talk about math. Okay, if you see a relationship like this, you can instantly understand the u is a function of S and V, right? So actually, T and P is actually the slope. So here, T is actually the slope, and minus P is actually the slope. Well, the slope. Okay, so now we know that the slope. Then partial U over partial S. If we do further the second derivative to the partial V, and for the other term, we do second derivative to partial S. Suppose U to partial S partial V, U to partial V partial S. They should be the same, right? They should be the same. This one should be equal to this one. So you can imagine that the T here, you can substitute T and substitute this here. So basically, partial T over partial V at constant S, and partial P over partial S on the constant V with the minus sign should be equal. Okay, should be equal. Okay, so we can obtain the extra information because of the mathematics techniques. Previously, we don't know T and P's relationship, but after we do the Maxwell relationship mathematic techniques, we can obtain partial T over partial V at constant S equal to minus partial P over partial S at constant V. Okay, so this is the extra information obtained thanks the help of the math. Okay, so each of the partial is a state variable that can be integrated along any convenient reversible path. Anyway, the thing is that we can obtain extra information. That's the help of this mathematic techniques. 好，我们要讲 Maxwell relationship 是什么意思呢？这个关系是什么？就是我们先不，我们还没有介绍 S 嘛，但没有关系，我们不要管它，我们只是看数学来看，只要看数学就好。假设你看到一个式子长这样子 ，du 变成 TdS minus PdV，那这时候你一定马上可以说 ，OK， 这个 u 是 S 跟 V 的函式，对吧？你看得出来啊，这样子，因为它是这两个共线，对不对哈？那这两个共线，你也可以知道，前面这个 T 其实就是它的斜率，后面这个负 P 就会是它的斜率。OK， 那这个斜率呢？看这里 ，partial U over partial S，partial U over partial V。那我们就去做第二个微分，我们把前面的做 V 微分，把后面的做 S 微分，就发现这两个东西其实长一模一样的啊，它们理论上来讲会要是相等的，对不对哈？那这时候我们再把这个东西带进去来看，这个东西带进去来看，我们就会发现， 哎，这个东西其实这个二次的微分其实就是 partial P 的一次的微分，那 P 的一次的微分。那既然这两个相等，这两个相等，然后左边跟右边又相等，表示说中间的也相等。那这个东西等于是说，我们原本不知道 T 跟负 P 之间的关系是什么，但是因为这样子的 Maxwell relationship，所以我们发现了，然后数学的技巧，我们就发现它们之间有更深一层的关系，多了一些原本我们不知道的资讯，这就是这个数学技术的帮助我们的地方。Okay, so yeah, that's a review one. Let's continue to review two. All right, review two. Review two. Thermodynamics solid. Yeah, the two. Come on. So previous one, and it's kind of chapter 5 in our textbook. All right. So proof of the Gay-Lussac dual experiment. Remember that in the review one, I said at that time, Gay-Lussac dual experiment, you just accept the condition, accept the conclusion. But now I'm going to prove that. Prove that. Okay, so let's imagine that for a reversal process, du equal to d bar q minus p dv. No problem. We have learned that, right? So you can imagine that every state from point A, well, point A to point B, you can always, in the PV diagram, you can always achieve that by a really general path to achieve that. For example, you start from point A and go the path process 1 with constant V, and then achieve the P you want, and then you control the pressure at constant pressure, and then change the volume to achieve the final state. Okay, so all the process can be decomposed into two general process, 1 and 2. Okay, so during this process 1 and process 2, du equal to cv dt, right? And process 2, du equal to cp dt minus vdp minus pdv. Okay, and because p is constant, so nothing here, right? And then what will it be if this is ideal gas? Remember the proof of the Gay-Lussac dual experiment is for ideal gas. Remember that, right? So we can introduce PV equal to MRT. PdV plus VdP equal to MRDT. Okay, so CPDT minus MRDT, and then equal to CP minus MR times dt. Okay, so process 1 and process 2 can be concluded here and here. So process 1, process 2, u is a function of t only, right? So this is from A to B, 1, 2. Okay, so for all the so this is only the one of the simple process. Okay, just one simple process from point A to B. simple. However, all reversible process here to here, and the path is like this. You can imagine that it can always be decomposed infinity. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Right? So they can be kind of digitalized. Right? So that's the reason why you can, how to say, extend your finding in such steps. In each step, you can always follow u is a function of t, and each small step can combine to any type of all reversal process. So this is the proof of Gay-Lussac dual experiment. OK， 好，我们要讲，还记得我们上一次讲到第5章，我们会证明 Gay-Lussac dual experiment 吗？哈，当时就是一个实验，他们发现，如果气体很接近理想的状态下的话，只是一个 function of t，OK， 那它的 internal energy 是 function of t。好，那这时候我们就来证明它。我们可以想象一个 reversal process， 它一个最简单的，它只有2个步骤，一个是上跟右，在这个 PV 图上，这一段当然就是 V 是 constant， 在这一段当然是 P 是 constant。那我们来看一下 V 的 constant 状态下，它就是 du 等于 CV 乘上 dt， 这个没有问题。那如果今天是 P 的部分的话，那 du 就会是 CP dt 减 VdP 减 PdV， 然后这边是因为是 P 为常数，所以就取消掉了。那这时候我们要看的是 ideal gas， 对吧？好，所以这个 P minus PdV 可以写成 NR dt， 啊，代入进去以后发现 process 2第二个过程它是 CP 减 NR dt， 那2个加起来我们就会发现，哦，它真的就是一个 function of t。好，但是呢只有一点点嘛，就是它就只有一个上跟右，那可以应用到全部，可以延伸到全多种的 process 吗？可以的，因为你看哦，虽然是 PV， 随便一个路径，但是其实所有的路径都可以把它变成小小的上跟右，上跟右，上跟右哦，所以说它都可以拆解成这样子。如果你所有的步骤都可以拆解成这样的话，那它 all reversible process 就是所有的可逆的反应都可以，只要是 ideal gas 的话，都可以使用上面的去拆解它，所以它就是 U 就是 T 的，只有是 T 的，只有跟 T 有关。OK， 这就是我第一个要跟大家介绍的东西。The second thing is that let's prove of 1 over t is a good integrating factor to make q as a exact function. Okay, let's take a look. So we know that the bar q equal to blah, 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 blah. Okay, and this is from review 1, page 13. Remember that? So this equation looks like ugly, but we have done that before. Review 1, P13. And Q, as you know, Q, the change of Q depending on path. So you can have the bar in the front, right? At the front. So can we divide by t, or we can say multiply 1 over t as a factor to make it d bar q over t? So, well, again, we can do other. We can try. We actually need to try 1 over t, 1 over v, 1 over t square, 1 over v square, dot, 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 dot. When you encounter engineering mathematics, when you took your course in engineering mathematics, when you talk about integrating factor, you need to try. You need to try different factor. The first one you should try is 1 over t, 1 over v, 1 over t square, 1 over v square, something like that. You try, but we found that the first one is okay, right? So why we can say this is okay? Because we find that this satisfies the condition we just discussed in the beginning of our lecture, right? So let's take a look. So d bar q over t, we try that. And of course, everything become 1 over t, 1 over t, no problem. Okay, and let's take a look. This is d z, right? And this is n, x and y, and this is d x plus n xy, and this is d y. Okay, so this one is n, this one is n. Okay, so let's continue. So we need to make it this one to do the differentiation, partial differentiation to y. Sorry, v. And this one need to do partial differentiation of t, which means that we are going to make it partial n over partial y, partial n over partial x. We are going to see if this equal sign held. We want to see that. Okay, we want to see that if this left hand side equal to right hand side. Okay, so let's continue. Partial u squared over partial v partial t cancel each other. Okay, so you see, partial u partial, so you can see this one to do this one and that one for that one. They can cancel each other, right? So only thing left is partial u partial v t and equal to t times partial p t minus v, partial p over partial t at constant v times t minus p. So here, anything left is here. Okay, if you after you cancel the second derivative term, and then for ideal gas, RT over P, RT over V is this one. So partial U over partial V at constant T. Here, remember that partial U over partial V at constant T, U is a function of T only, right? So this is 0, right? And this can also be substitute to this right-hand side, and you can see TR over P minus P equal to 0. So which means that, yes, the left-hand side and right-hand side are 0, all 0, so they can equal to each other, of course. So which means that the question mark can be taken out. Okay, the equal sign can be held. Okay， 好，现在要讲的就是我们来证明看看 1 over t 是一个好的 integrating factor。我们来看看，那什么叫做 integrating factor？ 还记得吗？就在我们的公式里面，在算 integrating factor 的时候，通常都是用式出来的。我们会通常是式 1 over t、1 over v、1 over t 平方这种东西去试。那今天运气好，第一个就试成功了。那还记得怎么样试成功吗？试成功的意思就是说， partial n over partial v partial n over partial v 会等于 partial n over partial x。如果它等于的话，我们就试成功了。OK， 好，我们就来看看。那首先我们除以 t 以后得到这个式子，得到这个式子以后呢，可以很明显的可以看到这个东西就是 m， 这个东西就是 n。好，那算完 dz 的以后呢，我们就去把前面去 partial v， 后面去 partial t， 来算算看。那这个等号到现在还不确定哦，哈，还不确定哦。我们只要画一个 question mark。那这时候呢，我们就开始算左边跟算右边。算左边、算右边，算完以后呢，我们就会发现它有一个 term 是重复的。好，这边有个 term 是重复的，会重复，它们就互相删除了。删除以后呢，就会留下这个东西跟这个东西。OK， 那这个东西算这个东西，cancel 以后，这两个东西会留下来。那我们还是不知道这个等号是多少，好，我不确定这等号会不会留下来哦，我们只是说左边跟右边，左边留下来是这个，右边留下来是这个。那左边很简单，左边它的 partial u over partial v， 还记得我们的 u 只是 t 的函数吗？它就会等于0咯。那我们就看接下来就看右边会不会等于0，右边会不会等于0啊？会啊 ，partial p over partial t 会等于多少？rv 嘛，对不对哈？所以 t 除以 t 乘 r 除以 v， 不就是 p 吗 ？t 减 p 等于0，所以两边都为0，所以它就会这个问号就可以拿掉了。OK， 表示说左边跟右边会相等。那相等什么意思呢？我的 1 over t 是一个好的 integrating factor， 我们成功的找到了。那它会怎么样？它会把我们的底坝 q 除以一个 t 以后，这个新的 z 新的函数会是 exact 的函数，就这样。那我们当然知道了，之后就会知道这个是其他的 properties。Okay, so so some question is that can we write the first law in terms of state variable only? You see, this is not state variable. It depends on path, right? It depends on path. So can we, and also second question, is there any state variable to distinguish between a reversible and irreversible process? Okay, let's take a look later. 这一章的意思就是说啊，我们能不能把第一热力学定律把它全部都写成 state variable， 也就是说 path independent， 我们只要关注它的起始或最终点就好了，因为 path dependent 太复杂了。那所以我们能不能找到一个东西是可以直接描述那个当下的状态，而不会去因为它的路径而有所影响？然后呢，那这个东西也可以顺便说，有没有这样的一个 state variable， 它可以去分辨可逆跟不可逆的过程？我们就想要知道这件事情。那接下来就知道其实就是 entropy。那接下来20分钟后我们再继续介绍。Okay, there will be a break. I will see you after 20 minutes and I will see you later. Okay, thank you. If you have any questions, just come here. Thank you. 说，聊到大哥的位置。现在加，其实你可以加，你知道吗？我不知道。你只要加，你以后你就先加上去，然后以后你都可以帮我加。OK。 Yes.
Make sure about if you want for
Yeah.
the example that of course I found the different value and different unit.
Different unit.
Because also science method could be right. It's textual, but you use the method or method
Mm,
or
so let's go back to your slide. It's Jewel. Yeah,
yeah.
that's great. Yeah, that is. Yes, it is. Work, right? Is the work. Work, of course. It's Jewel.
Oh, but it's
Yeah.
nine.
Sorry?
It's nine, right?
Sorry?
M.
3.
Oh, it's three.
This is 3. Is it? I'm sorry. Okay.
Okay.
You are right. Maybe it's not which this one. Okay.
Yeah.
Okay. Here, right?
Uh-huh.
It should be 3, right?
Uh-huh.
Wow, this is 3. This is 9, not 9. Sorry.好，哪一个？好，就是说，呃，我们要知道左边跟右边，希望要相等，但是我们还不确定，对不对？那这边我们就做微分，我们微分要先微分前面乘后面，再加保留前面，再微分后面嘛，对不对？这边这边有乘嘛，所以你要先对它乘，那这先对它微，再乘它，再加上保留前面，再微后面嘛，对不对？
就是
对吧？
先对它为
先对前面微，再对后面微。
嗯
OK，所以你会有一个这个项，二次项，这个也是，那这个也是先为前面，再为后面，这样。对啊，对啊，对啊，对啊，嗯、对啊，就是你必须要先为前面，然后再为后面，所以这边你要好好的把它写出来，列出来，然后这个东西会被消掉，消掉完以后会剩下这些，左边会剩下这个，右边会剩下这个，这样可以理解吗？好，这样 OK 的话，那接下来就是这边看，但等号还不能确定哦，等号还不能确定，好，这个等号还不能确定，这个等号还不能确定。那我们先看左边，左边会等于0，为什么呢？因为 U 是只有跟 T 跟有关，所以它 partial V 的话就完全就会等于0。那右边会等于0吗？会，因为 P 会等于 RT 除以 V 嘛，对不对？所以 RT 除以 V 对它做 T 对作为分，所以变成 R 除以 V，R 除以 V 再乘为 T 又变成 P 了，P 减 P 就等于0。对，左边会是0，右边会等于0，那0等于0，所以它这个问号就可以拿掉了。左边0这个吗？这是还记得前一页啊，就是这个 U 是 function of T only，所以 U 除以 U 对 V 来做微分的话，就会是为0。对。 Okay, welcome back. Okay, let's have a little chat. Right. Well, Google. So I want to show you some pictures. When I go to visit, go to US, we go with professors, each department head in different university. For example, I don't know if I can draw this. No, okay. So the left hand side is professor in Tsinghua University, 张守一老师, Professor Zhang. And the middle one is the right hand side is 林家峰老师，中兴吧，中兴。Anyway， 刘浩志老师 from Chenkong University, and 陈英杰老师 is from Tsinghua University as well. And the right hand side is the 吴子嘉老师 from Central University. Right? So seven professors, and right hand side is a postdoc. Sorry, is a PhD student, exchange student in Brown University. Sorry, MIT University. Okay, so we went there, and we talked with a lot of professors, and we go to see their lab. Their lab looks like this. What kind of lab in your place? Okay. The most impressed things I have ever seen is that they are extremely clean. Okay, extremely clean. I'm not saying that this is a good facility, expensive facility. No, I'm not saying this. I just amazed by their tidy. Okay, and I see a lot of sign out of the lab. They say no gloves outside of the lab. Have you done the same with your procedure? Okay, because I always walking around in this building, and sometimes I found students in this building wearing gloves, pushing the button of the drinking machine, water machine. Actually, I'm really angry about this. Okay, so the reason why you wear your gloves because you are doing something toxic, and you go out the lab with your gloves, and you push the buttons of the water machine. This is not acceptable. All right, and also I saw students eating in the lab. Do you think they will do this? This is a world-class lab. They won't eat inside. But I see students eat and drink in your lab. I don't think this is good. And also, this is the reason why we are not as good as them. Okay? So actually, I should ask you and your professor to maintain high quality of your lab like this. Okay? It's their lab. Their lab is always open by glass. The reason why they use glass is that they can be seen, because if you eat inside this glass, you'll feel shame and embarrassed, right? This is the reason why. And also, Samsung donate such amount of money to that. Cool. And yeah, you see, lab. You see their floor is shiny. You see that? So clean. So clean. So clean. They're all professional. That's the reason why they can comes up world-class results and publish in really good paper. See? Clean. 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 They are all bachelor students, undergrad students. You see? Bachelor students, all clean. And I mean the lab, of course, are so clean. I'm not saying that it's a new or old. No, it's not relative. The reason, the only thing that I mentioned is that they are all tidy and wearing the suit and goggles. That's they all follow the rule. Clean. Anything else? See, very clean, very tidy. Yeah, that's it. And you see, their office are all glass, which means that they can be viewed, they can be seen. Do you think your working space can be seen by others? Do you have such confidence that you can be seen, or we tend to hide our monitor? What do you think? OK，好，讲中文啊，就是啊，我在那边啊看完以后，我觉得为什么人家那么厉害？为什么人家就是 top university？为什么？因为他们非常的严谨，非常的把实验室的守则看得非常非常重。你可以看到它地板是光亮如新，还会闪亮的，然后都不会脏乱。然后我在很多地方都看到，我应该有照片，你有看到就是他们上面有写说不要有手套在外面。See? No PPE outside the lab. 没有手，就是它到处都有这个标示哦，都没有就不能有手套，不能有手套。为什么要有手套？因为有毒嘛，有毒你还拿出来。我曾经看过非常多次，尤其是这一道这一边的，然后我有看过我们自己的材料的老师不实验室的学生拿着手套就这样出来了，然后还穿着手套去按饮水机，我非常非常的生气，其实因为这在干嘛？这是傻子吗？有毒的东西你还拿去按，你毒自己就算，你还毒别人，我真的非常非常生气。好，所以我看到这个东西我非常非常生气，无法忍受。那所以说你看人家就是这样，我是不是应该弄一下贴？所以说，请各位同学一定要告诉自己的指导教授跟自己的同学们，你看到他的，你看到他戴着手套出门，绝对要跟他讲说不要耍白痴，好不好？因为这实在太蠢，我非常生气，我看到这我非常非常生气，当然我都忘记跟大家讲，所以不过不好意思啊，我们实验室是做实验的，所以我们没有这么多规则，但是各位是做实验的话，千万要注意，不要把毒带出来。我非常的生气，我看到那个真的是很糟糕。你看，人家就是这样子然后他们的地板很漂亮，很干净，都不会脏乱。我们看看我们自己的实验室是不是这样子？那就是我们可以从小地方就看得出来，到底谁可以做大事。所以我相信大家都知道该如何做好。然后还有什么？然后他们的那个办公室都是玻璃的，比方说我们就可以看到他在里面在干嘛。那我们有我不知道我们自己有没有这么的有自信，可以让大家知道，就是看得到我们平常工作的样子。那还有另外一个就是，他们刚刚有大学部的研究，就是实验室，你看到他们做实验也是非常的专业，戴着他们的手套，戴着他的 goggle，然后，对啊，真的是严谨啊，我只能说严谨，非常了不起。在哪里啊？看一下，大学的实验室真的是他们也很专业，在哪？找不到。Anyway，就是这样，对，就这样跟大家分享完了哈，所以我觉得这是很重要的一件事情。OK，那其实我很久以前就很想要，我其实很久以前就想要讲，但我每次都忘记就是我应该每一年都要跟大家讲一次，宣导一次这个观念。我的实验室有自己买一个饮水机，我的办公室我自己也有饮水机。为什么？就是因为我看到有同学拿着手套去按饮水机，按公用的饮水机，所以我就再也不用了，因为我觉得实在是太糟糕了。请大家不要做这种事。如果你看到你的实验室同学是这样子的话，一定要跟他讲，然后也要告诉你的老师，叫他好好的管学生，懂吗？加油，我们要一起让这件事情变更好，不要被读到了，到时候你们都喝到化学药剂，多恐怖啊！OK， right, so that's the thing I want to talk about. After seeing others' place, and then now seeing the good things in other university, I found that I need to tell you, I need to report to you the reason why they are good. Okay. Okay. Next one. Next one. Continue our lecture. So the answer of the previous page, the question in previous page is entropy. Okay, we are going to make inexact formulation exact. Let's do it. So du equal to d bar q minus d bar w. D bar q, d bar w are all path dependent, right? So for reversal process, d bar w divided by p equal to dv. So this makes inexact exact, right? Similarly, can we find d bar q divided by hello. Sorry, my computer run out of battery. Run out of power. Oh, stop recording. Okay, started. Good. Right, I'm sorry. Sorry. should be continued. Right. So similarly, d bar Q over T, we define that as a change of S. The S, of course, called entropy. S is a state variable because 1 over T is a good integrating factors. We have checked that. Of course, 1 over P is also a good integrating factor for WR, reversible process, right? Integrating factors, right? So we can write the first law, U equal to PdS minus PdV. Right, so the S is actually a measure of randomness of the internal motion of a system. Well, we will discuss this later. 熵就是一个可以帮助我们把第一运动定律第一热力学定律写成跟 path 没有关过程没有关系的一个式子，也就是说 S 是一个叫做 state variable 的东西。那 du 等于 d bar q 减 d bar w，d bar q 跟 d bar w 都 path dependent， 就是跟过程是有相关性的，所以说 w 除以 p 以后呢就变成 dv，v 就没有相关性了，对不对哈？那 q 除以 t 以后 s 就不会有相关，就不会跟过程有相关性了。1 over t 跟1 over p 都是好的 integrating factor， 因为它可以帮助我们把不 exact 变成 exact， 然后就把它写成这样子啦。然后 S 呢是一个跟随机性，它内部的随机性有关的东西，混乱性有关的东西。OK， 下一个。So let's talk about Carnot cycle. Carnot cycle is actually a simplified ideal cycle. Okay, so for example, I mean, all the cycle can be blah 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 blah, but we later blah 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 blah. But later we can always find it can be decomposed into small pieces of Carnot cycle. Okay, just like the step we talk about in our beginning of our lecture today, right? So the Carnot cycle is an ideal and kind of basic one step by step process. Okay, all the process can be decomposed into small combination of Carnot cycles. Okay, so let's focus on a tiny unit of the process, Carnot cycle. And the Carnot cycle is actually very ideal. So for ideal gas, right, use state variable, and therefore for a cycle like this, we can show a video for you to see there are four stage for this cycle. The first one is isothermal, and then adiabatic, and isothermal again, and adiabatic again. Go back to its original state. So it can be seen like teaching TS Carnot cycle. Go. Okay, the first stage, and then adiabatic, and again isothermal, and then go back to its original state by adiabatic again. Okay, so four stages can come in and come out of the Q2 and do the work. Okay, and we will examine each step later. Right. Okay, done. So let's continue. So this is the one we just showed you, and then we can examine the first one, Q2 and Q1. So you can imagine that because start from the U hasn't changed because it's a cyclic, right? So the U equal to 0. So which means that overall the bar Q equal to the bar W again, right? So just because this one, right? So Q1 equal to W1, Q2 equal to W2. You can something like that. Okay. Then let's talk about Q2 equal to W2, Q1 equal to W1. What does that mean? Because during the A and B process, the W2 equal to MRT2 natural log V over A. We learned that because we have read it, review 1, T10. So that's how we obtain this, right? So we discussed this before. So because W2 equal to Q2, so the value of the Q2 is this one, okay? And then this is greater than 0 because VB greater than VA. And the next step, we go back to C from C to D, and VC is greater than VD, so it makes the Q1 less than 0. Okay, and then we can yeah. So this is the one of the condition that we can get. Then and first stage and third stage we have examined here. How about BC? How about adiabatic? In adiabatic process, we also know that EV to gamma equal to a constant. So we can also write down for B and C state, which is nRT divided by V, and V gamma equal to mRT V gamma minus 1 equal to a constant, right? So E2 V B gamma minus 1 equal to P1 because N and R cancel, right? P1 VC gamma equal gamma minus 1. They should be constant, right? So we can write down this. And then for the fourth stage, T2 VA gamma minus 1 equal to T1 VD gamma minus 1. Okay, so you can imagine that we are talking about process 1, 2, 3, 4, and this is 1, 3, and this is 2, 4 stage. Okay, so each of them we can yeah, we just can get this. And if we do this one, divide T2 divided by T2, T1 divided by T1, and then we can obtain that VB divided by VA equal to VC divided by VD. Okay, and don't you think they look familiar? yellow part, right? Yellow part. By connecting these two, we can have Q1 divided by Q2 and minus T1 divided by T2. Okay, that's it. That's it. So Q1, Q2 can be further combined. Q2 divided by T2 plus Q1 minus divided by T1 equal to 0. So that's the Carnot cycle tell us the Q2, Q1 and the temperature relationship equal to 0. And this is ideal case. 好 Carnot cycle 这个循环呢，它其实是一个很标准化的、很简化的一个很一般性的一个过程。好，那为什么要这样做？是因为所有的 reversal process 都可以用这个来去拼凑出来，就好像是之前我们讲的上跟右这样子的process， 它可以把它组成所有的形态，所以这边就把它当做是一个小单位了哈。那以后要处理其他的形态都可以这样做，所以这就是为什么这个 Carnot cycle 我们要特别拿来提的这个东西。那因为它是一个理想化的 cycle， 所以呢，它是一个 cycle 嘛哈，所以它的 U 不会变，因为它从头到尾是从头跟尾的状态是一样的，所以它的底 U 跟底bar Q 跟底 bar W 会是相等的，这没有问题。好，然后呢，这边 Q1 跟 Q2 是分别为第一个跟第三个过程。那Q2 跟 W2，会在第一过程里面 Q2 跟 W2 是相等的。那 W2 是多少呢？它在 Review 1的第10页我们有讲到 W2 可以用这样子来表示。那 W 可以用这样子的式子来表示，所以呢 E3 这个状态就可以写出这个式子。那 VB 跟 VA 的大小的比值，它会让它这边会等于大于0。那第二部分就是小于0，这应该没有问题。好，这是E3的状态。那24的状态是 adiabatic， 我们一样在之前也有上过 PV 的 V 的伽马次方会是一个常数。那 B 跟 C 是在同一个 adiabatic 的状态嘛，对不对哈？等压的过程状态，所以说它们会相等，它会是相等的。那所以我们就把刚刚的式子写出来 ，T2、T1 啊，这是 T2 嘛，这是 T1 嘛，对不对哈？那VB 跟 VC 在这里，他们会是符合这个式子的 ，OK， 所以是第二个过程，第四个过程也可以如法炮制写出来。那我们就除以一下，我们就把这个删掉了，就发现它会有这样的式子。那这个式子跟上面这个黄色部分还蛮像的，所以呢，我们把这个带进去，我们就可以得到一个式子，就是 Q1 除以 Q2 会等于负 T1 除以 T2。那再把这个式子继续往下写，就可以得到这个式子。也就是说 ，Carnot cycle 有一个很重要的特征，就是这个东西。Carnot cycle 是 ideal 的哦，是理想的哦哈，所以这边会等于0。那下一页就会讲它不理想的状态下会怎么样。Okay, next we are going to talk about Carnot cycle is not ideal. When the situation is not ideal, what will happen? Now, Clausius inequality, as we mentioned that Carnot cycle is a kind of tiny step for all type of reversible cycle. So, for example, this is a random selected reversible cycle, and we found that for all kind of reversible cycles, we can divide them into small little Carnot cycle. Small. Okay, for a small Carnot cycle, Q2 and Q1 become infinitesimal small step. So Q2 become a tiny step, Q1 become a tiny step too. So Q2 and Q1 adding a small tiny step debug. Okay, so debug Q2, debug Q1 equal to 0. You can see this step debug Q2, this step debug Q1. All right, and then you can draw them. Wow, every step, every small step. You can always decompose random cycle into many small corner cycle, and luckily you see this go down, right? And this is go up, and this is go down, this is go up, this is go down. So which means that they cancel each other. Okay, so nothing happened during the adiabatic because they all cancel each other. So a reversible cycle, reversible general cycle, general. You can say it should be summation for all debug Qi, Ei, right? All type of debug Q, debug Q2, debug Q1, debug Q3, debug Q4, 5, 6, 7, blah, 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 blah. Okay, so this is all kind of debug Qi divided by Ti. So you can imagine that it can also be written down as debug QR divided by T. And it will be 0, right? Because every pair of them equal to 0. 1 and 2 plus them together become 0. 3 and 4 equal to 0. So everything times out together becomes 0. Okay, so here notice that I write it down here as there's a R. It's called reversible. Okay, right. And then you can sort of, okay, reversible. R means reversible. All right. And now this is reversible, ideal, right? Good. However, how about irreversible? How about irreversible? And then we notice that this Q1 over Q2, well, here we have an efficiency definition. Well, it's a little bit long, so I'll ask you to just read the textbook, section 5.3 in textbook, the efficiency, eta equal to 1 plus Q1 over Q2. Okay, this is the definition of efficiency. So reversible, of course, has better efficiency than irreversible. That makes sense, right? So reversible Q1, Q2, because one is all the same. One for all the cases are the same. So Q1 over Q2 will greater than Q1 plus over Q2 plus. The plus here indicates the irreversible cycles Q1, Q2. Okay, so this is definitely greater than that because they has higher efficiency. Okay, then we know that Q1 over Q2 equal to minus T1 over T2. Yeah, so we can replace this one less than minus T1, T2, and we do, we make T1 to the bottom and Q2 or go to the top, and then make this one to the right hand side become plus. So you can see that Q2 plus divided by T2 plus Q1 divided by T1 less than 0. Okay? Then remember that our previous Carnot cycle is, Q2 over T2 plus Q1 over T1 equal to 0. This is reversible ideal case. And then for small one, you add in the bar here. So now we can also, for a small Carnot cycle, for small irreversible cycle is the bar as well, right? Again, write down that every irreversible cycle is really similar to what we look at, the bar Q1 be less than 0. So you can compare this one and that one. Okay? So summing that together. So you can see in the world, we have ideal one and non-ideal one process. So reversible process and irreversible process. Summing that together, generally we can say, okay, the bar Q divided by T less or equal to 0. Okay? So this is always correct in the world. Okay? Either reversible becomes 0, either irreversible less than 0. So this one is always correct. Okay, always correct.好，要讲的 Clausius inequality 就不等式，可拉西俄斯不等式啊，谁也不知道怎么翻译哈。那总之就是所有的 reversible 的 cycle 可逆的反应都可以把它拆解成小的 Carnot cycle， 小的 Carnot cycle。刚刚的 Carnot cycle 是大 cycle 嘛，所以它的 Q2 除以 T2 加 Q1 除以 T1 等于0。那小的的话，我们就可以想象它这个非常的小，所以只是 debug Q2 debug Q1，所以我们就把它写成这样子啦。好，这没有问题。好，我们把它拆解成这些，那一上一下，一上一下，一上一下，它们就会消掉，对不对哈？所以说我们就只剩下这些小边缘，OK？ 那你如果说这边叫做 debug Q1， 这边叫做 debug Q2， 我们可以说这边是 debug Q3、Q4、Q5、Q6， 大概是这样。那所以说全部的 reversible cycle 加起来，其实就是所有的小小的 debug Qi 加起来。那实际上也就是做一个 cycle 的积分，把这全部都积起来，然后除以 t 嘛哈，然后等于0。哦，就这样，因为它这边等于0嘛，2等于0，全部加起来当然全部都会等于0 ，OK？ 所以这边等于0了，没有问题。那接下来我们就要看 irreversible 的，我们都可以知道 reversible 一定是比较 ideal 的状态，理想状态，所以它的效率一定会比较高。那 irreversible 一定表示说它有一些 loss， 对不对哈？所以它的效率一定比较低。那 efficiency 的这个定义正好是1加 Q1 除以 Q2， 那这个东西，也蛮简单的哈，你就说起来比较长，你就回去看一下书本，它的 efficiency 的定义会是1加 Q1 除以 Q2。好，那既然 reversible 的效率会比较高 ，irreversible 效率比较低，所以说它一定会大于它 ，OK？ 因为这边1是不变的嘛，啊，所以 Q1、Q2 的 irreversible 状态一定会大于 irreversible 的状态。那 irreversible 的 Q1、Q2 我们加了一个 plan 给它 ，OK？ 好，然后 Q1、Q2 等于多少？前面这一页有，当然，所以呢，我们就直接把这个会小于这个东西。那接下来呢，我们就把 T2，不对 ，T1 拿到 Q1 的下面 ，Q2 拿到 T2 的上面， 然后呢，再把这个负的移到左边去变成加，就得到这个式子小于0。那刚刚又说了，这个东西是一个大的 corner cycle irreversible 的 cycle。那如果今天把它变成小的呢，一样就把前面加个小 d bar 就好了。所以呢，这个东西写成这样，所以其实跟这个东西你可以比较一下，人家等于0，这边小于0。然后呢，再一样画葫芦的把它写出来，然后呢就可以发现 reversible 是长这样子。irreversible 是长这样子，一个等于0，一个小于0。那这时候世界上所有的 cycle 要么 reversible，要么 irreversible，所以呢加在一起，我们的 debug Q3T 这 cyclic 的积分就会是小于或等于0，就这样。好 ，next one. So let's continue. So debug Q will always less or equal to 0. And we also think all the process can be treated either irreversible or reversible. So maybe we can make it simpler, make it simple again. So 1 to 2 state is reversible, and 2 to 1 is reversible. It's just simplified. It's just an example. Don't worry about that. And of course, this is a cyclic integration. So 1 to 2 is irreversible. 2 to 1 is reversible, right? So how about we just rearrange a little bit? 2, 1. Debug Q over T. And if we change reversible part to 2, 1, debug QR over T, don't you think here we change the order of it? We need to give a minus sign, right? Or we can just make it go to the unequal sign to the other side of the unequal sign. So the minus sign can be deleted. Okay? And then we notice that QR, the bar QR over T from 1 to 2 is actually the definition of S2 minus S1. Okay? So this is a change of entropy for 2 states. So the bar Q over T is always less or equal to ds. So ds is always greater or equal to d bar Q over T. So the equal sign for the reversible process. So now this is really important. ds, S2 minus S1, is always greater or equal to 0. Okay, this is really important that the entropy of an isolated system never decreases. Isolated system means debug Q 0, right? So delta S will always greater or equal to 0. So that's explain why the entropy try to getting bigger and bigger, which means that all the systems are going to make it more random as it possible. OK， 好，那我们的 second law 可以继续写下去哈，就是刚刚讲到这个会等于小于等于0，对不对哈？那这时候我们又来把它简单化。我们说这个东西很简单，就是1到2这个状态，要么就是 irreversible， 要么就是 reversible process。就这两个，我们就1到2是这样，那是 irreversible， 2到1是 reversible。反正它就是一个很 general 一般化的一个假设啦哈。好，1到2是长这样，2到1长这样子，会小于0，没有问题。那接下来前面是 irreversible， 后面是 reversible， 然后呢，我们就把它看一下，我们把2跟1 反过来好不好？变成1跟2，那这边就要加一个负号咯，啊，这边要加一个负号。那这时候负号再把它移到小于等于的右边，就变成负号就抵消掉了，所以就变成这个会小于这个。OK， 那右边这个东西就是 reversible， 它因为它没有任何的 dissipation 嘛，对不对？所以 S2 跟 S1 的状态相减，正好就会等于它这边的差值。好啦，那这时候就可以看到这个东西会等于 S2 减 S1， 那也就是说这个的差值就是 ds 会小于等于底 q 底 bar q 除以 t。 OK， 那当然了 equal sign 就是等于是它的 reversible process。 好，那这时候我们就说啊，如果今天有一个绝热系统底 bar q 会等于0，表示说 ds 会大于等于0，也就是说在绝热的系统状态下 delta s 就永远都会一直变大这样子，s 就会一直变大，差距就会变大，那表示说它会一直想要变得更 random 的意思。 OK，the next one I guess I need to give you a break 10 minutes later. Okay, if you have any questions, just come here. Thank you very much. See you later.
So maybe I could look for someone else. In other department. Yeah.
And announce, not only, considering my limited with my lab.
Okay, so like in that department.
Yeah, how can you do that? How to announce?
Actually, so for a group, there is NYCU group. So
Yeah.
They also ask for civil police from actually outside the department. All we also already just takes it as well. Okay, because there is a kind of convention for it to. Like. Yeah, yeah.
That's.
Okay.
So I asked all my students.
But I think we'll be a problem. I mean, at the end, we your science, so we agree actually.
Of course, but. They'll be, the most,
Yeah.
one.
Yeah, but then they will look like screaming at. That's the thing. Yeah, I need to find someone capable.
Yeah.
Understanding.
Really.
Yeah,
That's what it is.
okay, so no problem, I appreciate your help. I'll try to do it as soon as possible.
Yeah, okay. Hope you can find the.
Thank you so much.
喂，Welcome back。好，这一次出访啊，就是5天，然后第一天也不是5天啊，应该说7天，那就一大堆时间都在飞来飞去。我们礼拜天的晚上抵达美国，然后就要开车去，就直接去饭店直接睡觉了哈。然后第二天早上要开2个半小时的车去 UIUC，然后 UIUC 就一直开会，然后见学生到6点多，然后再开2个多小时回去睡觉。第二天去西北大学，又是一整天的行程，到下午，然后就直接坐飞机到机场去，然后坐飞机到 Boston 波士顿，然后到了波士顿就已经晚上了，就睡觉。第二天早上起床就去 MIT，又到下午，那下午呢又开车到 Brown University 那边，又要开1个半小时去那边睡觉，然后第二天又一整天的行程在 Brown，然后到晚上因为有晚宴，然后又回到饭店睡觉。第二天早上又去 Brown 开会，开完会以后又开车1个多小时回到 MIT，然后见学生，见完学生，终于有购物的行程了。几分钟？30分钟。30分钟完以后，又开车去机场，然后就回来了。所以我觉得我们是有史以来最精实的参访团。你有没有看到一些那种？我不知道你有没有听过以前那种政府的参访团，然后会写报告，对不对？我不知道你有没有听过一个，可能是你们小时候吧的那个新闻，就是那个新闻上面写妖兽爽。我看看有听过这个新闻吗？就是政府的参访团的出国报告上面写妖兽爽。我们这个是妖兽的精史都没有时间，然后最后30分钟，我就赶快去想要买纪念品，我也会就是给我家人这样，然后我到最后就去超商买了洋芋片，然后还有一些玩具，回来给我自己的家人这样。所以哇，我们的这一次的参访真的是非常非常精实，非常非常累，那很有趣那我以为参访团可以就是轻松，就没想到这么的累，对，超累的。好，I just talk about this Taiwan delegation group to visit universities. The agenda should be very easygoing. I thought I can have some very leisure time, but turns out the agenda or schedule for all the university really tight. Okay, they all give us many schedules in each university. All the university send the professor discuss with us one by one. Okay, one by one. Each professor has 30 minutes discussion. So there are many professors one by one. So just like interview us. So every day. We're really tired, really tired. But this is also show that all the university are really respect the group from Taiwan. The reason why they do that because they said Taiwanese students have really good performance when study abroad in the university. Okay, so they really think they need to pay respect and all their time to discuss with us, to ask us to send the best students to their university. So I can see that their respect and their time, they spend a lot of time on us. They show the respect to us. So which means that Taiwanese students are really good, okay, compared to other international students. Taiwanese students are good. So don't how to say that? Don't look down yourself. You are good, okay? You are competitive. 哎，我刚刚好像中文没有讲到这一段，就是为什么他们会花那么多时间，就我们的行程为什么那么紧缩？那是因那么紧，原因是因为他们非常的重视我们，他们派不同的教授一个一个跟我们聊天哦，所以我们像是被车轮战的口试一样。然后有一些 professor 是超大的，是非常的有名的。那所以说，我们好像被口试一样，很恐怖，我们压力很大。但是他们为什么会这样做？原因是因为他告诉我们，台湾的学员在那边表现非常的好，他希望我们的多派一些学生，如果有意愿的话，有兴趣的话去那边学习，会让就是对彼此都很好，双赢的状态这样。所以不要妄自菲薄哈，我们台湾的学生的表现，他们说很少有负面的，真的很少，所以我觉得这是一个很值得鼓励的事情。那大家可以想想看。那其实讲真的啦哈，我以前小时候，我去牛津大学，那时候我就觉得说，哇，牛津好学校，旁边都是天才吧，都很厉害吧。然后我就带着很紧张的心情，压力很大去那边，就过了1、2年，发现，哎，其实我们也不错啊，就是那边也很多需要我帮助的地方，很多同学都需要来问我问题，或是我要教他们事情，所以我觉得，哎，好像台湾的学生，然后我自己也觉得，我以前大学的同学其实都比我厉害，我也不是最厉害的，那所以其实我在想，其实台湾的学生真的是非常的聪明，而且态度都不错，希望了哈。那总之就是去到那边，他们都很喜欢，所以他们就花很多时间来跟我们聊天，来谈合作，来谈 program， 看能不能送学生过去，就是达到双赢的效果。所以我觉得很不错啦。哦，那大家加油，不要妄自菲薄。Okay, just telling that because they respect too much, so our schedule are really tight. I don't have any shopping schedule. I only have 30 minutes to shop. So that's a little bit tired. This is enhanced delegation group, delegation activities. Okay, right. Let's continue our lecture. So we just talk about the entropy behavior. It will be increased all the time. So although the net entropy always increase, never decreases, but the part of system can decrease. Well, you can see that in the next sentences. It's always possible to decompose the change in entropy into 2 parts. The first part is system part. The other is surrounding part. Okay, and they are the interface between system and surrounding. So they will exchange the entropy. The delta ST plan is the entropy transfer across the boundary during the core process. So which means that across the system and surrounding. So delta S and delta ST plan actually they are different sign. Positive or negative, okay? But delta S and delta S plan is actually, delta S is the system, the system change entropy itself, okay? And delta S plan is also the surrounding change itself, okay? So when they sum it all together, they will cancel each other. So the only thing left is delta universe is this part and that part. Of course, the net entropy change will greater than equal to 0. That's it. So that's what they want to say. Okay, the itself delta S itself they changed, always greater than equal to 0。好，这边讲就是说，我们不是都是说entropy 必须要变大吗？不会变小。那但是实际上个体本身可能会变小，那当然是要看状况了。但这里我觉得有点难。总之呢，在数学上来说这是可行的，原因是因为呢 delta S system 跟 delta S surrounding 是系统跟外部之间还有一个边界，这个边界他们会互相交换它的 entropy， 就是他们的 transfer 的across the boundary。那这交换的时候，当然交换过去跟交换过来是一模一样的 ，delta ST， 他们是不同的正负号，他们会抵消掉，所以加总起来呢，他们虽然他们
好，谢谢。
OK， 好，总之他们加总起来会大于等于0，对，他们会消掉。但是呢，因为他们是 different sign， 所以说他们加在自己的部分可能会 delta system 会变小，可能delta surrounding 可能会变小，没有错。那是因为他们自己加在这边的正负号加在一起可能会变化，但是全部 total 加起来的时候 ，different sign 会被消掉以后 ，delta S 加 delta S plan 一定会大于等于0。OK，next entropy and available energy. Heat can be converted to mechanical work. We all know that. So heat can be converted to the work, no problem. However, in the real life, we need to times efficiency, right? The efficiency, eta equal to 1 plus Q1 over Q2. Again, this is the definition in the textbook. And also, we have another formulation, 1 minus T1 over T2. We obtain this in P6, page 6, right? So we can say the bar Q times 1 minus T1 over T2, okay? And then you can notice that the available energy which can fully transfer to the bar W is the bar Q times 1 minus T1 over T2. And the unavailable is T1 over T2. And then when they sum it up together, become the bar Q, right? So the available energy always decreases in a irreversible cycle. Of course, you see that because irreversible cycle has loss of energy. And you can treat that increasing entropy is actually the energies degrade into forms that are more difficult to use, which is actually unavailable. So energy disappear? No, they are still there, but they are less easy to use, more difficult to use. Okay, right, that's it. Another thing is that entropy is a measure of the randomness of the internal motion of a system. So you can imagine that there are many particles or molecules or atoms in a system. So more randomness means higher entropy by means of statistical. We will discuss this more later. OK， 好，有点累了。熵跟可以用的能量，我们都知道，热可以把它转换成机械能、机械功。那当然不可能是完美100%转换，所以一定会乘上一个 efficiency 的这个 factor。那么乘上去以后呢，就会变成1加 Q1 over Q2。那这个东西我们刚刚讲过，在 section 5.3的书里面。那我们在第6页，我们就把这个 Q1 又把它转换成 minus T1 over T2， 这是我们在第6页的时候讲到的。所以我们说 available energy 什么意思啊？就是我们这个 energy 可以转换成功的，可以被用的，就是这个了。OK， 那不能被用的就是那个，这两个加起来就是原本的 debug Q。那这个 unavailable energy 什么意思呢？它不见了吗？不是，它还在，只是人比较难用而已啊，比较难用而已。如果今天人类科技超级发达，可以把 unavailable 就是不好用的能量再度把它抓回来用，那就不会是 unavailable。OK， 但是它总之就是 entropy 一直就是会一直增加的原因，就是它只是把东西变成能量变得更难用而已。更难被人类使用而已。那另外一个 entropy 的解释就是它是物品系统里面的颗粒或是分子或是原子等等。那它越随机越混乱 ，entropy 就越高。那这个东西其实是在统计热力学里面会更讲到。那之后我们会讲，会提得更清楚。忽然变得好累了，可能时差也有关系吧。OK， 接下来next one combine the first and second laws. So reversal process, we know that du equal to d bar qr minus d bar wr. You know that, right? We noticed that the reverse process are here. Okay, so just give you a. All right, and this equal to TdS minus PdV, no problem. But the first law in the general form is du equal to d bar Q minus d bar W, which is a little bit different from this. Okay, so we say this is 1, equation 1. And we say the first law, general form. General form means that we didn't specify reversible or irreversible. So this is a general form. The general form, of course, we know that review 1, P3, and this is a P4 in this page, this PDF. Okay, the second law is that TdS equal to d bar QR greater than d bar Q. This is page 7. What we learn in page 7. What will it looks like? We can further extend that d bar QR equal to d bar Q plus epsilon. Although d bar QR is greater than d bar Q, but if we make an equal sign, which means that we can just add it the dissipated work become unavailable energy, right? So we say this is equation 3. Then if we substitute 3 to 1, and we can get du equal to d bar q plus epsilon minus d bar, wr. If we substitute the first equation, we can obtain equation 4. The equation 4 become irreversible. Now. Okay? It becomes irreversible now because we adding the irreversible part into the reversible part. So it becomes irreversible now. Then let's compare. Let's compare 4 and 2. We notice that 4 and 2 compare d bar w equal to d bar w r minus epsilon. This is equation 5. So, of course, you can say the dissipated work appears as a heat, typically, okay? Unavailable energy, like heat that we cannot use. So, we can rewrite first law in general form by state variables that the u equal to, let's take a look, pink. This is the bar Q. This is the bar Q. This is the bar Q. And this is the bar W, the bar W, and the bar W. All right. So if we sum them all together, it becomes the bar QR minus epsilon and minus the bar WR minus epsilon. Okay. And interestingly, this is equation 3 and equation 5, right? And we notice that they can cancel each other. Okay. So luckily, even we consider irreversible, we still can write du equal to TdS minus PdV. Okay, this is lucky. This is purely coincidence. This is general. But you cannot say TdS equal to the bar Q. You cannot say minus PdV equals to the bar W, because they containing epsilon. Okay, although they cancel each other, they individually no. Okay, they cannot connect it individually, but somehow together we still can write it du equal to TdS minus PdV. Okay, let's combine first and second law. OK， 中文我们要尝试把第一跟第二结合起来。那我们都知道，一开始的时候的 reversal process 的时候，我们 du 可以写成 PdS 减 PdV。OK， 我们在第4页的时候写到了。 那为了要把它写清楚一点，我们这边加 R， 说明它是 reversible 的状态。好，接下来呢，第一定律它是 general 的哦，它没有说它是 reversible 或不是 reversible， 没说，那时候没说嘛，对不对哈？所以 du 等于 d bar q 减 d bar w， 所以你看到这两个东西是不一样的哦，是不一样的。那我们可以把这个东西写下去吗？需要一些计算，这是我们在 review 1 P3 的时候写的。Second 是 P7，第7页我们写到 TDS 会等于 d bar QR， 然后它会大于 d bar Q， 是 reversible 的会大于irreversible 的。好，然后呢，如果这边这个大于，那我们就写说，我们因为知道 irreversible 有一些 dissipated work， 所以我们只要把它加回去，我们就可以写等于了嘛，对不对哈？写下去了，这是第3个式子。我们比较第3跟第1个式子，我们就会发现，其实我们的 d bar q 啊可以写成这样子咯 d bar q 加 epsilon， 这是第4个式子。那第4个式子再跟第2个式子比较起来，我们就会发现 d bar w 会等于 d bar r 减 epsilon。这 epsilon 其实就可以说明是说，这 dissipated work 其实就是 appears heat， 就是废热啦。这个热我们用不到，它太热就散掉了，用不到。它被消散掉，废热。好，那这时候我们的第3跟第5就可以把它写下来，我们就会发现 du 粉红色的变成 d bar qr 减 epsilon， 我们的蓝色就变成 d bar wr 减 epsilon。我们发现在这个式里面，它竟然可以消掉了，消掉完以后又等于 TdS 减 PdV 了，哇，真好，运气很不错。我们 du 呢写成 TdS 减 PdV。原本以为是 reversible 的，但是碰巧它的 dissipated work 可以删除掉，所以 du 也可以写成这样子。它是 general 哦，它没有说一定要是 reversible process， 它也可以适用。但是呢，第1项跟第2项它不能分开说，这就等于它哦，不行，因为它有 epsilon 在这边 ，OK， 所以个别来看是不能相等，但加起来就 OK 啊，这边要小心一点。Next one, I would like to let you note that internal energy U and enthalpy H have the table like this. In review 1, we talked about that before, right? Remember that we substitute this here, and we can obtain the result like du equal to cv dt, right? And dh equal to cp dt. Remember this, right? Review 1, and we're not going too deep here because we talked about that before. All we need to do here is that I would like you to emphasize this, highlight this. These 2 equations, and we will use that later. OK， 这个内能 U 跟enthalpy H 这个东西的表，我们在 review 1都已经写过了啊，这边我都讲很多次了哈。那这边我只是要提醒你，这有2个重要的式子，叫做 du 等于 cv dt，dh 等于 cp dt， 这2个东西请 highlight 起来，我们等一下会用到。OK， 这就是为什么等一下会用到了啊，所以我现在才提起。好累，怎么那么累？你知道这一趟行程，我们有一个行程里面是参加一个 Sustainable Energy 的论坛，叫做在 Brown University。那有请到谁呢？朱棣文，棣就是我这个棣，他是诺贝尔奖得主哦。然后他在上面可以给大家看一下朱棣文。 朱棣文是哪一位呢？我们看一下哦。诺贝尔奖得主，诺贝尔奖得主，这个朱棣文，好，他是物理的，很厉害。这样，然后就讲了，你就给他照相。然后呢，晚上的时候发现他跟我们住同一个饭店呢。然后呢，不知道怎么回去，所以我们就要带他回去。所以呢，然后我又是最年轻的，所以他就说年轻的带路，然后我就帮他带路，然后带路走回去，带他走回去路这样，然后我帮他，我们张照片，反正我就帮他按那个，就是跟他说，哎，这边走，啊，这边就要小心，因为他有点老，有点年纪了，然后要带他走路这样，啊，很有荣幸，然后我就被照相，就是说我帮他按那个过人行道、过斑马线要按那个红绿灯的嘛，哦，cross the street，然后我就被照下来了，然后我就传讯息给爸妈说，哎，你看你儿子帮诺贝尔奖得主的合照跟按那个，结果他们就说我看起来像保镖，像卫士，因为穿西装嘛，按那个，对，还蛮有趣的，right，然后还带着他回去。你看这些人都是大佬，很厉害的人，然后我就在前面带领他们走回去，其实我压力很大哎。如果今天走错路的话，一群人跟着你走，然后他们又是尽量不要走，因为他们很老，所以有点年纪了。如果带他走多一点路的话，他们就会很生，就是我对他们不好意思，这样压力蛮大的。好，就这样，哎。Okay, just talk about that guy is a Nobel Prize winner, Stephen Zhu. Okay, and because I'm the youngest faculty there, and we accidentally live in the same hotel, so I need to lead them to the hotel. So I need to guide them and remind them the gap, and also push the cross street button for them. My parents think I'm a bodyguard of the uh, Nobel Prize winner. Okay, next one. Entropy change in reversible process. dr equal to du plus p dv, no problem. And we just divide by over t, sorry, divide by t to make it entropy, right? So ds equal to d bar qrt over t and everything like this. And we say this is equation 1. All right. And later we will use this. And then we can examine all, we will summarize all the entropy change in different process. The first one is adiabatic process. Adiabatic process means that there's no heat, right? So no heat. So ds equal to 0. So s equal to constant. So you see a reversible adiabatic process is an isentropic process. What is isentropic? Isentropic is that S is constant, all right? Entropy doesn't change. But you need to be reversible. That's very difficult for us to achieve. An isothermal process means that the T here can be taken out of the integrating sign. So it can be written as 1 over T and 2, 1 d bar QR, right? So this one QR. So QR over T, and then we name it, we learned it in page 7 as well. No problem. Then The third process we're going to discuss is that isothermal and isobaric change of phase. What does that mean? It means that we are discussing the entropy change during the phase transition. What is phase transition? Remember that we have this line, right? We are focusing on this process, okay? During this process, S2 minus S1, S2 minus, sorry, 1 and 2. S2 minus S1 equal to L divided by T. The L is the latent heat, okay? So the L is actually the d bar Q is the heat required for phase change. Okay, so this is latent heat. Then the third one, isochoric process. What is isochoric process? Which means that V is constant. Okay, V is constant. So again, U is the V and T function. And V is constant, which means that U equal to U of U is only function of T. So actually, this is similar to an ideal gas. Okay, so this also leads to du equal to Cv dt. Okay, so isochoric process, the change of U is Cv dt, and highlight, right? Highlight as a yellow, we mentioned in the previous page. And then, so 1 with the V equal to 0, what will it be? The equation 1 in the beginning of this page, which is S2 minus S1 equal to 1, 2 CV 2 CV dt over T. Okay, so if you want to see the entropy change in isochoric reversible process, it can be written down as Cv dt over T and doing integration from 1 to 2. OK， 好，我们要讲的是，现在我们要一一的去讨论，在不同状况、不同过程下 ，entropy 是怎么样改变的。OK， 那 general 的式子长这样子，没有问题，我们写成 equation 1。好，那这时候adiabatic process 就是绝热的状态下 QR 等于0所以说你的 entropy 也会等于0，entropy 的改变也会等于0，所以呢就是 S 等于 constant，S 是常数，也就是说在 reversible 的绝热的过程中，它正好也叫做等熵过程等熵的过程当然有点难了好，那接下来呢 isothermal process 在等温的状态下，运气好的就是 T 可以拿到积分符号外面，所以它 S2 减 S1 正好就等于是 QR， 所以 T 我们在第7页有得到同样的答案。接下来要讲的是 isothermal and isobaric change of phase， 什么意思呢？就是在等温的状态下，也等压的状态下，是怎么样entropy 是怎么样变化？那这个东西基本上就是相变的时候，这个平台就是 P 会是常数的时候，等温线上，所以说正好就是符合这个趋势。那在这个状态里面，的 d bar Q 正好就是 phase change 就是相变化需要的能量，那就是我们的潜热咯。 所以呢 L 除以 T 没有问题。接下来 isochoric process 是什么意思呢？是体积等于常数，体积没有变化。我们都知道 U internal energy 内能它是 V 跟 T 的函式。那如果 V 是常数的话，那就等于是 U 只有是温度的函式。哎，那这不就是跟理想气体有一样的行为吗？啊，所以说在这样的状态下，它的 entropy change 可以使用 du 等于 Cv dt 来帮助我们计算。那这个就是那个黄色的前面这一页的公式了哈。那这时候我们的 S2 减 S1 再拿这个上面来看，因为底 V 会等于0嘛哈，所以你的 ds 就会是 du over t 的值。那 du 又等于 Cv dt， 你就可以用 Cv 除以 t 的积分来算出它的 entropy 的差别。OK， 啊，没有能量了。哦，好饿哦！你知道我的老师，那就是刚刚的那个叫什么？刚刚那个参访团里面有一个我的指导教授，你知道吗？谢宗林老师是我的指导教授。谢宗林老师，哎，谢宗老师不在这里，因为他当照片，他当这位谢宗老师，他是台大材料系的谢宗林老师，我以前曾经被他共同指导过，然后他第一眼看到我就说：“嘿，年弟，你变胖了。”第一句话是这样讲，然后对，所以就好减肥，赶快减肥吧。结果现在好饿哦，而且我不是跟你讲过，我如果饿的话，我心情会很不好。对，我心情会很不好。哎，我跟你讲过，我饿的时候心情会不好，有是做大肠镜嘛，对不对？哎，我跟你讲过，对吧？心情会变得非常不好。然后，而且我饿的时候会很明显，我的手就会抖，然后就没有力气了这样子。所以我现在就是这种状态，我好累啊，还有8分钟，好，我的意志力需要我撑下去，加油！来，这是 sorry continue. We have another process that we cannot we didn't discuss. So continue. We bring up the first equation here. Okay, nothing new. And then we talk about isobaric process. Isobaric process, you know that it must be related to CP, right? Because CP is measured under constant P, which is isobaric, right? And then if we talk about CP, we must talk about H. We know that review 1P14. Okay, when we talk about CP, it definitely related to H. H equal to U plus PV and DH du PdV VdP, no problem. And then we know that this du plus PdV is d bar QR, right? If you see equation here, right? du PdV du PdV, okay? d bar QR and VdP. Okay, so everything becomes simpler. D bar QR divided by T equal to DH over T minus V over T dP. Okay, isobaric process dP equal to 0. And then H is a function of T and P, but now constant P, there's no function of P, no variables for P. So again, dH equal to Cp dt. The yellow high line we mentioned. So it become equal to the bar QR. Okay. So it said S2 minus 1 equal to 1, 2 CP T over T. Right. So very similar to the previous one, but now it's CP. 好，最后一个 process 我们还没有讨论到的就是 isobaric process， 就是定压的过程。我们把刚刚那个第一个式子拿回来这里，好，我们没有改变任何东西啊，我们只拿过来。接下来 isobaric process 定压一定跟我们的 CP 有关，因为 CP 就是在定压下量测出来的材料性质。跟 CP 有关的是谁啊 ？H 在第14页，Review 1的第14页就有知道 ，H 等于 U 加 PV， 它的变化量就会长这样子。那把这个式子跟这个式子相比较一下，我们就会发现这个东西其实就是底坝 QR。那这时候我们把底坝 QR 除以 T 以后呢，就是 ds 啦，对不对哈？然后其他的也除以 T。那运气好，底 P 等于0啊，因为它是 isobaric process。然后呢，我们的 H 呢就跟 P 无关了，因为 P 不会变，所以 H 是 function of T， 是 T 的函式。那这时候就跟我们前面一样啦，改变的 DH， 改变的 H 会跟 CP 乘上底 T， 那这个就会就可以得到底 QR。那我们把 S2 减 S1 做积分起来，就可以用 CP 来帮助我们得到 S2 减 S1 的值了。OK， 剩下3分钟。Next one， entropy change for an ideal gas. Ideal gas can tell us the first one, du equal to Cv dt because u is a function of t only, right? So du equal to Cv dt. This is the first one. Ideal gas can tell us. The second thing is that, of course, PV equal to RT. There's no n here because it divided by V divided by n becomes small v. Okay, so two things ideal gas can tell us. So for reversal process, ds equal to the bar QR divided by T, which is the U divided by T plus T divided by T dV. Okay, that's all we know. And then continue. So du equal to Cv dt. Okay. And then we can say Pu over T is R. Okay. 1 and 2. Dun, dun, dun. Okay. What we should do here is that we do integration for everything. And then we can get S2 minus S1 equal to Cv natural log T2 over T1 plus R natural log V2 over V1. Okay, so if Cv is a constant, we can get out of the integrating sign and then we can get this result. So, yeah. Now, let's take a look. In the classical thermodynamics, we always calculate delta S, S2 minus S1. So we cannot assign entropy value for certain state 1 or state 2. But statistical thermodynamics can do that. They are good, they are better. Classical can only focus on change of the entropy. Okay, and yeah, this is something we can note that. And then if we examine this we can find that if temperature increased, T2 greater than T1, the entropy increased. And if volume become greater, entropy also increase. Okay, we can see this from here. OK， 翻译，如果是 ideal gas 理想气体的话，它会给我们 du 等于 cv 底 t 这一句，然后还有 pv equal to mRt， 这个没有问题。有这式子的话，我们把前面的式子做积分，去取代一下，就可以得到 S2 减 S1 会等于这个东西。那这东西可以告诉我们，增加温度、增加体积都可以增加 S。然后另外一个重点在于，我们在传统热力学里面只能看它的差值，但是在 static 就统计热力学的话，我们就可以给 S1 是多少 ，S2 是多少。OK， right， done. Thank you very much. I'm so tired. I'm going to have a good lunch. Bye bye. If you have any questions, just come here. Thank you. Bye.